Hi, I'm Daniel Chan from UNSW Sydney. This is Extension 3 Mathematics for talented high school students. In this video, I want to talk to you about the exponential generating function. So this is a variant of the usual generating function, and for some problems, it encodes information about the corresponding sequence in a much nicer way. So let's go to the definition for what the exponential generating function is firstly. So suppose we're given a sequence A0, A1, A2, and so forth of complex numbers. We can use these to construct the following exponential generating function, which again is some power series. And the coefficients will depend on this sequence. And what are the coefficients of this power series? The coefficient of x to the n is just an on n factorial. So this is very, very similar to the usual generating function. In the usual generating function, you don't have the n factorial term in this denominator here. You just have the sum of an x to the n. Let's have a look at some simple examples, okay? And for this first example, I'm going to have to use the notation of a perm S, which is a set of permutations of S, or mathematically, one way to describe it is just a set of all bijections phi from S to S. Okay, so you can think of this as a permutation of S. Okay, so in this first example, what I'm doing is I'm going to let an, I'm going to look at the set, remember this here is just the set consisting of integers 1, 2, up to n. I'm going to look at permutations of this. And how many elements are there? What's the cardinality of this? The cardinality of this is, of course, just the number of permutations of 1 up to n is just n factorial. So if an equals n factorial, then in this case a tilde of x is going to be, here you've got these n factorials in here, n factorial over n factorial x to the n. So this is just a geometric series. You just have these ones here. So you're just looking at powers of this. So you have 1 on 1 minus x. So whereas with the usual exponential generating function, you won't have this n factorial in the denominator, then you'll have this power series here, which actually doesn't converge except when x equals 0. Here we've changed the coefficients by dividing them by these factorial terms, and now we have a nice convergent power series, at least whenever the modulus of x is less than 1. Okay, so let's have another look at an example. So suppose bn is equal to 1 for all n equals for n rather. Then what do you have? Then all of these terms are just 1. These an's are just 1 here. Then this b tilde of x, this exponential generating function for this sequence, this constant sequence here. Well, what you'll see here when an is equal to 1 is just the exponential function e of x. And that's the reason why this is called the exponential generating function, because when you have the constant sequence 1, you just get the exponential function here. Okay, so I want to give you an example of a time where it's actually quite convenient to use the exponential generating function. And what's that? Okay, we're going to look at the notion of what a derangement is. And this is probably a notion that you've seen before. For example, when you have a Kris Kringle, okay, what's the point of that? So you have a group of friends, suppose you have n friends, and what you want to do is you want to make sure that each person, okay, each friend gives a present to a different person, and you want to give it in such a way that everyone receives a present as well. Okay, so for example, if you have 4 people, 1, 2, 3, 4, maybe person 1 gives a present to person 2, person 2 gives a present to person 3, person 3 gives a present to person 4, and person 4 gives a present to person 1, okay? But one thing that you don't want, for example, is something like this. 1 goes to 2, 2 goes to 3, 3 goes to 1, and 4 buys a present for him or herself, okay? So what can you, how do you mathematically describe the situation of this type of present giving, okay? So this you can think of as a type of map from this set of 4 people back to this set of 4 people, okay? it's a function. Okay, each person has to give a present to someone else. So it sends a person to the person that he or she is giving the present to. Okay, so it's a function like that. And you want to make sure that everyone gets a present, so this function should be surjective. And the other thing that you want is that, of course, if it's surjective, it should also be injective. And the last thing is that, well, you don't end up with someone giving a present to themselves. Okay, so what you have here is, of course, you have a surjective and injective function, so that's a bijection. So a derangement of S is going to be sigma, an element of this set of permutations, so it's a bijection from S to S, with the extra property that basically no one gives a present to themselves. So that means that sigma of S actually moves S to something else. It doesn't equal S. Okay, so that's the definition of a derangement. So we know if we look at the cardinality of this permutations of S, and S has a finite number of elements, like it's just this set n here, square bracket n with n elements, then this is n factorial. But it's interesting to ask, well, what's the number of derangements? How many of those permutations are such that you actually move every single element? So that's the question here. What's dn equal to the number of derangements of this set here? Okay. To work this out, of course, if you know what its exponential generating function is, then you would have answered this question as well. And what I want to show you is that it's actually quite easy to compute what the exponential generating function of it is. Let me show you now how to find the exponential generating function d tilde of x of the number of derangements of this set n. And what's the way we're going to do that? So it's quite interesting. Firstly, let's just focus our attention on a single permutation of the set 1 up to n, not necessarily a derangement. So there you have a set sigma here. So maybe if n equals 4, you have a set like this, 1, 2, 3, 4. What I'm going to do is I'm going to break up this set into two parts. Okay, it's going to be a disjoint union of two parts. So let's just pick a particular example for sigma here. Maybe it swaps 1 and 2. Okay, and it leaves 3 and 4. It just sends them back to itself. Okay, so that's clearly a permutation. You just swap 1 and 2 and leave 3 and 4 fixed. Okay, so in general for the sigma, we can break it up into two parts. A part where sigma doesn't do anything. Okay, it just sends. So you're looking at all the integers I in this interval, such as sigma of I equals I. So here it will be the fixed part will include 3 and 4. Sigma sends 3 to 3, 4 to 4. Okay, they're the ones which are fixed, but it moves 1 and 2. Okay, so this fixed part, it doesn't do anything. Okay, it's the identity, so to speak. And what does it do on the other part? It actually moves every element in the other part. Okay, so it's actually a derangement on the other part. Okay, so now let's count the number of permutations. Okay, so we're going to count it in a rather interesting way, which is going to tell us about the number of derangements. Okay, so in the first example, I use an to note the number of permutations of this n. So this is defined to be n factorial. And I'm going to count this in a rather interesting way. Okay, so what I'm going to do is the following. So what I'm going to do is that, well, given any permutation, what I can do is I can say, firstly, I'm going to break it up according to how big this fixed set is. Okay, so this fixed set, maybe nothing is fixed. Okay, k equals 0 in that case, where nothing's fixed, and that means that you have a derangement. Okay, and the other extreme is where you have everything is fixed, so this is the whole set. Okay, so we're going to look at the size of that. So k is going to go from 0 up to n. And the other thing I looked at is the sequence where everything is 1. So I'm going to look at the sequence where this is always 1. Okay, so I'm going to write it down like this. That's my sequence, constant sequence 1 that I had in the first example. Okay, so if I've done that, okay, suppose I've fixed k elements, then that sigma, which fixes k elements, it has a derangement of the other n minus k. And how many ways are there of deranging those n minus k? That's d n minus k. Okay. So if I fix k elements of this set to fix, then the number of permutations that fix those k elements is going to be d n minus k. Now, of course, there's a lot of choice for which k elements that I pick to fix. And the number of choices of that is n choose k. So if I sum this up from k equals 0 up to n, so this sum will depend on how many elements sigma fixes, then I will get the total number of permutations. Okay, I would have counted each permutation once. Okay, so basically, how do I count all the permutations here to get the n factorial? Firstly, I say I'm going to pick, okay, how many elements get fixed by this permutation. That number varies from 0 to n, so that's my k. And then I'm going to say which of the k elements of this n get fixed. So there's n choose k possibilities there. Remember, this bk is just equal to 1, so there's n choose k possibilities there. And then I fix those k, and then I have to move the other n minus k. So that's the number of derangements of n minus k things. So that's d n minus k. And so when you form this sum, you'll get n factorial. Okay, so now what we're going to do is, when you look at this, this looks a lot like the coefficients that you get in the Cauchy product. So what I'm going to do is I'm going to multiply the exponential generating function of this sequence of derangements, so this d tilde x, with the exponential sequence that we got from this bk sequence, which is this constant sequence of 1s. Okay, so let's just have a look at that. So we're going to look at b tilde of x times d tilde of x. So what's that equal to? So let's just write down the formula for this. So you're multiplying. Okay, so the formula for this is you look at k equals 0 up to infinity of bk on k factorial x to the k times the sum from j equals 0 to infinity of dj on j factorial x to the j. And let's work out what this product is. You just take the Cauchy product of these two, and that will tell you what the answer is. So that's a sum from n equals 0 to infinity of, well, it's a power series, so what's the coefficient of x to the n? Well, you use the Cauchy product formula. Okay, so it's going to be the sum from k equals 0 up to n. So you pick the kth term here, bk, on k factorial over d n minus k on n minus k factorial. And let's just have a look at this coefficient here. Okay, so what does this coefficient equal? This coefficient here, if you look at this expression here, this looks a lot like this, but instead of this binomial coefficient n choose k, you just have in the denominator k factorial times n minus k factorial, which is also the denominator that appears here. What's missing between the two terms is just the n factorial in the numerator. Okay, so what you have here is just an on n factorial. And so at the end of the day, what this is equal to is, well, if you look at this, this is basically just the definition of the exponential generating function for this sequence here, a tilde of x. So if we look at the constant sequence here, okay, that gives us a generating function, an exponential generating function rather, b tilde of x. If we look at the sequence of derangements of this set n here, okay, that gives us a sequence, and we get an exponential generating function. When we multiply them, what do we get? We get the exponential generating function for the sequence giving the number of permutations of n. And so now we can work out what this d tilde of x is, because we know what b tilde of x is and a tilde of x is. They're things that we already worked out in the first part. Okay, so what we find here now is that therefore d tilde of x is equal to, so this one here, remember this is a sequence of ones and that gives us the exponential function, so we divide to the other side, so it's just e to the minus x on 1 minus x. And this gives us a lovely way to count the number of derangements of a finite set. I hope now you can also use exponential generating functions in your enumerative problems.